So now I'd like to introduce our speakers. Unfortunately, Tahir couldn't make it. So our speakers for tonight would be Joel and Robin. So Joel is a mechanical engineer and the National MVHR Solutions Engineer at Fantech, Australia. He's passionate about delivering energy efficient, healthy, ventilated buildings. Joel is also the current Deputy Chair of Australian Passive House Association. So he would be speaking after Robin Phipps, who's a professor of building science and program director of the building science programs at the Schools of Architecture and Design at Victoria, Wellington. She has done extensive research on performance of homes, schools, and offices, including heating, ventilation, and energy efficiency, and low carbon buildings. So let me invite Robin to start off with her presentations.
Good evening, everybody. Just checking that you can see the slides.
Yep.
And hear them.
Yes, we can see the slides.
Okay. Thank you very much, Bibin, for inviting me to give this presentation. I'm going to give a quick run through about some of the research that we've done. It's going to be reasonably high level and not a lot of detail. So I'll just sort of fly through a number of topics. And if anything in particular grabs your attention that you'd like to know more about in the longer term, please feel free to contact me. It's easy enough to find me on the Victoria University website. I'm going to talk a bit about our research and the health effects of cold homes, and then I'll move on to talking about ventilation. This photo here was one that I took 2 weeks ago when I was staying in a serviced apartment in Auckland. It wasn't a shabby establishment by all stretch of the imagination, but you can see the profound, extensive mold that was growing on the window frame. But not only are fancy apartments mouldy, we have 45% of New Zealand homes have visible mold. It's quite likely a lot more have mold that is concealed within the wall or in the roof or the underfloor cavity, which aren't counted in this 45%, which was a figure generated by brands. This is a concern because molds can lead to allergies and inflammation of the lungs and other respiratory conditions. Not all molds are a problem, but some are very toxigenic. So it's a bit like if you're thinking about the feline family. You know, you might be happy having a tabby curled up at the end of your bed, but you certainly wouldn't want a lion. And so the same thing with molds, that some are might be just an irritant, where others can cause cancer or can grow in your lungs and are very hard to get rid of. And this is one of the causes or one of the contributors to why New Zealand has one of the highest rates of asthma in the OECD. So we tend to either be the first or the second, depending on which way it gets counted in terms of our asthma score. Now, we might like to be first in the world in cricket and rugby, but being first in the world for asthma is definitely something that we should be highly ashamed of, and we should be doing a lot to get rid of. The drug bill alone is $4 billion per year. And with 1 of 4 children having asthma, we know that when a child has an asthma attack, they're typically off school for 4 days. And that a few episodes of that leads to a lifelong educational disadvantage. New Zealand also has a very curious excess winter mortality, which is not seen in other countries around the world. And so what this excess winter mortality is a big terminology, which is saying that for some reason, more people die in the months of winter even when you take out car crashes and other things that would occur during the winter months. Quite a significant number of people. So it could well be somebody who is got some health vulnerabilities, might die in winter, where if they hadn't been in a cold, damp home, they may have had more years of life. We also have one of the highest rates of COPD, previously known as emphysema. COPD is coronary obstructive pulmonary disease, which leads to a very high level of morbidity. So your lungs basically become concrete and they can't inflate and deflate properly, leading to oxygen deprivation. Has an early onset, particularly in Polynesian and Pacifica families, of about 55 years of age, where in European families, even in New Zealand, it has an onset of about 65. So very, very hard condition to live with, and there is very little that can be done about it. And part of this is thought to be caused by our high rates of allergy to mold and to dust mites. Dust mites are ubiquitous as are molds in New Zealand homes. The highest rates are often found in bedrooms and bedding, and it's quite typical that the average pillow, if it's 10 years old or more, 20% of the weight of that pillow will be dust mite feces, which is a good reason to go out and buy a whole lot of new pillows this weekend. I don't have shares in pillows. We also have a problem with the affordability of energy. So the New Zealand housing stock was designed primarily on the premise of cheap hydro energy. And so our building codes, when modelling was done on the cost of heating versus the cost of insulation, it was considered that energy was so cheap that we didn't actually need to have insulation. Obviously, this is no longer the case, and especially when we take in more conditions such as health into the equation when we are working at how to design the thermal performance of the building envelope. We need to really strongly challenge this concept of cheap energy. For one, the cost of all energies are growing faster than the CPI and have done for a long time, and this is going to predicted that it will increase. And we have another problem looming, that with the electrification of transport systems and the demand that this is putting on for electricity, there's going to be more problems with peak generation. And as a result of that, we're going to need a lot more generation brought onto the grid. Whatever type of generation you bring on, it will have embodied carbon and carbon emissions to it. So even when, if there was a new hydro situation brought on board, a hydro dam, the damming of a valley would create a lot of carbon emissions. And we also have a lot of fuel poverty and fuel hardship. And this is seen as something which is increasing. In the previous census, the decision, if you can call it that, to have no heating was the fastest type of heating choice, if it's a choice. And this was most commonly experienced in solo parent families. So choice is probably not the right word. It's probably more a Hobson's choice. So there's an urgency to upgrade the existing building stock with better thermal and energy performance and solutions which are not going to push people further into economic hardship. A reasonably old statistic now, but in 2001, $250 million was spent by the average household to be freezing. So not by the average household, it was spent by households to be freezing. And with the measurement work that we have done, we found that the average New Zealand household the mean temperature, so this doesn't include the fact that it could be warm during the day and have very low temperatures overnight, is 4 to 6 degrees below what the WHO has stipulated as the minimum health guidelines. And in some of the measurement that we've done, we've found children's bedrooms in particular down to as low as 3 degrees. And that's the equivalent of, that's colder than your fridge. So it's kind of like, come on, darling, take your teddy. We're going to pop you into the fridge for the night. It's not what many parents would be wanting to say, but it is the reality of what many will be doing tonight on a beautiful, clear sky night that we've got. So we do know from the public health work and a lot of work done by the respiratory physicians that when we've got temperatures, indoor temperatures below 16 degrees, it's going to impair respiratory function. Temperatures below 12 degrees is going to generate cardiac strain and strain on the circulation system. But we also know that when people are living in low temperatures, they tend to confine themselves to bed where they can stay warm, or they may only heat one room and not the whole house. So they go into a bit of a thermal shock when they need to move out into the bathroom. And there's many families who will huddle in the lounge room, put mattresses on the floor, and everybody will sleep in the lounge room for the winter. This leads to social isolation. And when we can improve the warmth of a home, one of the things that gets reported very quickly is we were more social. We could actually go out and see people, or we could have friends over because we weren't so ashamed or confined in our home. And we also know that when we've got low temperatures, it's going to lead to dampness and to mold growth, and that will, not in addition to the health effects, it's going to lead to deterioration of the building materials. So that's increased maintenance that needs to be done. So it's a bit of a downward spiral. Quite some years ago, the Hikainga Oranga Healthy Housing Research Group did what was it then a landmark study on insulation, housing and health. And in this study, they took 1,000 homes that were all built with minimal insulation, and they retrofitted where they could get access to it, insulation in the ceiling and the subfloor. And what they found was that prior to insulation, an uninsulated home is about 1 degree warmer than outside. So if it's 3 degrees outside tonight, it's going to be 4 degrees in the home without adding any heating. But when we put a little bit of insulation in, it brought the temperature up by about 1 degree. There was a saving of 19% in terms of the energy use. So there was both a combination of increased temperature and energy saving. There was a lot less mold, but possibly most importantly, the exposure to high relative humidities, that is RH above 70%, reduced by about 2 hours per day. And it's thought that it was the change in RH, or the reduction in high exposure to high RH, was what was really important in bringing about some health effects. And these improvements included, if you were an adult, you had fewer days off work for sick leave. If you were a child, you had fewer days off school, which also benefited their caregivers. Very significantly, there were fewer hospitalisation admissions for respiratory conditions and GP visits. And it was this line where it costs roughly $1,000, $2,000 a night for a bed stay for a respiratory condition. And it costs not much more than that to insulate a home. So it's a bit of a no-brainer for the warm-up home campaigns, which have been running by successive governments to fund insulation in homes. We used a very similar methodology to the insulation study for the heating study. And in this, we enrolled 406 homes where there was an asthmatic child. And these homes were used where we had homes with an unflued gas heater or a small portable electric heater. And we enrolled them into a study where half the homes were given a brand new heater, either a heat pump, a flue gas heater, or a wood pellet burner, and the other homes were given that a year later. And in this study, we did a subset of these homes, about 60 of them, where we did some very intensive monitoring. We were looking at the environmental conditions in these homes. The results of this study said that the children in the households with the new type of heater had 50% less disturbance for wheezing and nighttime coughing, a lot less lower respiratory symptoms, really significantly 1.8 days less off school per year, and fewer doctor's visits. And when people did get sick, it was for a shorter period of time, and as well as there were less episodes of illness for respiratory infection. But this is just to show you a couple of the bits of data from the intensive monitoring. And so what we've got along the bottom here is the flue gas heater, the heat pump, the wood pellet burner, an unflue gas heater. We had a couple of wood burner heaters sneak into the study, surprisingly. And on the far right, we had one household which was all radiant heaters used very extensively. And the surprising thing was that the heat pumps were struggling to get to 18 degrees. Most of them kind of got close. The wood burners were warm. The unflue gas heaters were way too cold. And if you just hold that in your head, that these households were way too cold. But then when we look at what were the pollution levels in these homes, if you had a portable electric heater, no pollution generated. If you had an unflue gas heater, the orange numbers were the exceedances of the guidelines. So a lot too much nitrogen dioxide, too much formaldehyde, huge levels of CO2, and even carbon monoxide was present with some of these heaters. Quite significant amounts of CO, given that we should have zero of this inside a home. But when we compare that to the heat pump and the flue gas heater and the wood pellet burner, there were no exceedances, apart from one flue gas heater had some fault in it that we struggled to find. So if we just move quickly on to ventilation and some of the studies we've done, I like to show this graph here because this tells a very sobering story. And this is ambient CO2 levels over a period of time. And when I started measuring CO2 levels, we could pretty accurately get CO2 levels outside at about the 350 parts per million in New Zealand. Now we are over 400 parts per million in the ambient. And so what this means is that when we're trying to ventilate inside, we've got less, we've got a higher concentration of CO2 outdoors. So it means that we need a higher CO2 level, a higher ventilation rate in order to get the same level of dilution. One of the studies we did, we called Ventilate to Educate. And we did this because we'd done some work looking at CO2 levels in classrooms. And we found that there were very, very high levels, often over 5,000 parts per million. We found that teachers, 40% of teachers never opened their classroom windows. They're too busy, the windows don't open, the hardware doesn't work, a whole heap of reasons why that wouldn't happen. And in addition to that, schools have got capped energy budgets, which mean that they can't cope with the energy penalty of opening windows and having winter heating escape. So we worked out that the school day is pretty much aligned with maximum solar radiation. And so classrooms are a bit of a low-hanging fruit in order to bring solar air heating in. We started off designing a solar air heater and realized it was a little bit trickier than we first thought. And we imported some from Denmark in order to do this study. And so this is shown on the roof of the classrooms here. It's a 3 meter by 1 meter panel with perforated backplate. And inside the panel is just a black felt with polycarb on the front and a small PV panel to drive the fan. We had 6 pairs of matching classrooms, one treatment, one a control. The treatment classroom had their solar air heater operational, and the control classroom had theirs disabled, and they switched over each school term. We put these on classrooms in Palmerston North, and we monitored them for 2 winters. We chose Palmerston North because it's about the midpoint of New Zealand. We didn't want the best or the worst conditions to show this up. And this was the PhD project recently completed of now Dr. Wu Wang. What we found was when we looked at the unoccupied classroom, so we were taking out the impact of what heater use and what the teachers and children were doing, we found that the solar air heater was generating heat above 18 degrees for 3/4 of the school hours, and that we were able to get a temperature gain of about 6 degrees or more for most of the school day. We had a good airflow rate at a good temperature, but this was not sufficient to dilute the CO2 levels in the classroom. But it was completely free heat, and it was dry heat. And this is just a couple of the publications that we have come out from this. The second publication is really interesting because we found that the particle levels inside the classrooms where the heater was being used were quite significantly lower than in the control classrooms, and the extent of that benefit was bigger than we expected it to be. Now, one of the things that we had a bit of a problem with in this study was that in every classroom we had $9,000 worth of kit, which wasn't covered by insurance. It required a lot of checking to make sure it was working. But more complicated was finding a space in a classroom where there were power points, we weren't in direct sunlight or directly in the way of a door, where we could install the equipment. And the lack of insurance was something that didn't make me sleep too well, because we had this here for 2 years. So one of the things we did was that we redesigned an Internet of Things connected sensor platform, and we created something which was much smaller. It can attach to the wall. It uses the same quality of sensors as we were using in the $9,000 setup, but we were making this for a fraction of the cost. It was also internet connected, so the data was being sent to us remotely. And we were very fortunate to win an NZIOB Innovation Award for this. And this is some of the team who helped with the development of it. But there were a lot of computer science students, product development students, and mechanical engineers involved in this little project. We use these for measuring indoor air quality in classrooms in Dunedin, Christchurch and Hawke's Bay. And what surprised us was that we found the highest levels of CO2 in summer. And what was happening was that the teachers were keeping classrooms sealed tight and running the heat pumps for cooling both summer and winter, and that the windows were very seldom being opened. So we were getting thermal comfort, kind of, but we were certainly not getting indoor air quality. And so this is just some of the data that we had, where we had some classrooms where we had very high exceedances of temperature, up to 97% over 24 degrees for some of the time. And we had some very high levels of relative humidity. The CO2, we should be in the green band ideally. And we had some classrooms where we had very high exceedances for 2/3 of the time. Now, work that's been done by Harvard University is showing the impact of 1 degree difference in temperature has a big impact on cognitive performance. And a 5 degree, when you can drop the CO2 levels below 1,000 parts per million, you can get a significant improvement in cognitive performance as well. So following on and expanding this work that's been done overseas, we have one of our PhD students, Lara Toki, who is looking at cognitive performance under different CO2 levels. And she's going to be running tests using EEGs and standardized cognitive tests when we step up through different CO2 levels. So this is results that are currently in the making, and we'll be able to report these at some point in the near future. We also have another student who's optimizing the solar air heater that we had tested previously. So we've gone back to the drawing board. We're using a New Zealand developed system, a very clever inventor from New Zealand. And we have just received all the components from overseas this week, and we'll be about to start building this system. And we have another PhD student, Clement, a very clever engineer, who is testing a combination of windows with trickle ventilation with a shape memory alloy built into the window, so it closes when it gets under 12 degrees, complete with a heat recovery unit, and he's going to combine that with a solar air heater. We've done some work on developing, in addition to the previous sensor platform that we developed, we call this Skimobo Plus, which has got a sad or a happy face depending on the indoor air quality conditions which are found in the classroom. And this is to give real-time feedback and to look at behaviour change. And we've done a STEM project for education of students where we can do some basic experiments looking at ventilation, temperature and relative humidity. And we call this room in a box with a few sensors so that some maths and science can be done easily by students. So we engage their minds early on. So that's just a very, very quick run through about some of the work that we've been doing with the whole focus is on about warm, ventilated and dry buildings and working towards carbon neutral. Do you want me to take questions now, Bibbin, or hold those to the end?
I think it would be better to hold the questions for the end. Yeah. Yep. Thanks for the presentation, Robin, and that was pretty cool and was informative. Thank you. And I'd like to invite Joel for his presentation. Now, Joel, please.
Beautiful. Thanks, Robin. Can you see that okay, Bevan?
Yep, it's all good.
Beautiful. I'll just bring it up a size. All good. Well, Robin certainly set the scene in terms of some of the issues we've got in buildings, whether they be schools or residential homes. And I come to you today from Australia, and the results aren't too much different here. We probably don't have quite the same degree of underheating in our buildings, and I think maybe that stems back to some earlier code requirements for heating, but we certainly have the same sorts of ventilation problems. So I'm going to step you through some of the problems and some of the solutions that will hopefully help make your life a little bit easier. So Robin's touched on some of the undesirable things that end up in your buildings, but they include volatile organic compounds, which are things that can come out of your furnishings. So anything that's sort of made out of plastics or plasticizers and synthetic materials has got a risk of off-gassing. You've obviously got moisture generation and so forth from cooking and showering, odours and things, allergens from dust mites. We've got particulates that can come from indoors or outdoors, and we've got CO2, as Robin mentioned. So the consequences, mould. We touched on those. These are actually a couple of photos from a client recently who's sent these through and said, what can I do? It's a relatively new apartment building. If you look really closely, you can even see that it's a double glazing window set up there, but clearly the frames aren't really exciting on those, and there's quite a bit of moisture landing in the building that's not being removed and turning into mould. Fine particles, so they can either be internally generated, so things like cooking, frying and so forth will generate internal particles. The dust you bring in on your shoes that ends up in carpets, but equally fine particles can come from external sources. So dust in the environment, living near traffic, you get tyre, some micro particles from tyre wear, brake dust and all those sorts of things. So VOCs we did talk about, but in a little more detail, sprays, finishes, all those sorts of things can give you some health issues, and such as fatigue and headaches and bits and pieces. Robin also touched on CO2 levels, and just to add to that a little, typically closed window environments are going to give you a rapid increase in CO2 when you have occupants indoors. There's essentially no dilution of that going on, whereas a mechanical solution at least gives you some ongoing fresh air and dilution. So as Robin also said, about 1,000 ppms for CO2 is about what you consider as the threshold for acceptable indoor air quality. Interestingly, CO2 is also often used as the proxy or a marker for good indoor air quality. So we know if we're controlling CO2 at a reasonable level, we're also probably doing okay with VOCs and other contaminants like that, that might be a little bit harder to measure, but at least based on that CO2, we can derive that some ventilation is in fact occurring. So ventilation is a solution to some of these problems. It's really the basis on which building codes for Australia and New Zealand have been built. So rather than put a magic machine in your buildings that absorbs all these things, the process has always been to bring outside air into the building and remove, ideally, those contaminants close to the source. So when you're cooking via a rain shorter in your bathroom, it might be that excess moisture. And typically building codes have offered a couple of methods for ventilating. So one of those being window ventilation and the other being mechanical ventilation. No surprises in all that. How do windows perform? So this is a study actually done overseas recently, where they picked 4 very similar apartments that had families living in them, and 2 of those had some mechanical ventilation. So in this case, actually whole of house heat recovery systems, and 2 of them had just standard bathroom exhaust, and both had operable windows. Now, they weren't given any particular instructions about window operation. They were just told to live as they would normally live in those spaces. But the 2 ventilation systems were obviously running and at different levels. Now, they've run them for approximately a year, this study. And if we look on the right-hand side, we can see these carpet plots. Now, really what that is trying to show the proportion of times that CO2 levels were above and below that 1,000 ppm mark. Obviously, exceedance is shown in red, such that you can see for the systems, the apartment, without some mechanical ventilation, that the airing or the opening of windows was not significantly high, nor was it in any of them, only at sort of that 7-8% of hours, and that the CO2 levels were really elevated in those buildings without some mechanical ventilation. So it paints a pretty stark picture of the types of indoor air quality that happen when you don't use sufficient window ventilation, and we'll touch on some of the reasons in a minute why that might not be occurring. So limiting factors for window performance. So again, in theory, open windows, nice bit of breeze, some fresh outside air conditions could give you reasonable ventilation. And I use the word could because there's actually a lot of factors that impact whether that's going to occur. Some of these are thermal factors. So what's the outdoor temperature like? Am I going to get really hot or cold by keeping my windows open? Is it too humid? Is the air velocity going to be too much? Is it really windy outside and is stuff going to blow around my house? What about the dust levels for outside? What about other pollutants? And is it noisy? And the last one I haven't put on there is, are there actually some security risks? And if we look at this image here, we can see a lot of those things apply. We've got noisy environment. We've probably got a security risk, keeping a window open on that ground floor level there. And finally, occupant behaviour. Whilst all the conditions might be okay, are occupants actually going to remember to open and close things? And do they actually know that that's the recommended approach? So there's a lot of factors that impact how well windows are going to deliver ventilation. If we look at the second alternative, which is some mechanical ventilation, and by mechanical ventilation, we can mean something as simple as bathroom exhaust fans. So they're extracting air and by consequence needing air to come in through the building somewhere else, or make up air if we like. That's sort of your basic starting point, but today we're going to have a little bit more of a look at mechanical ventilation with heat recovery. And this is what a typical system would look like. You've essentially got what's known as an HRV unit, heat recovery ventilator, and then you've got a network of duct and grills. If you have a little bit of a look there, you can see red and blue arrows, the blue indicating supply zones. So essentially we're going to supply a certain amount of air into habitable spaces, and we're going to extract the equivalent amount of air out of wet or odorous spaces. And so why are we doing this? Well, really, it's all about indoor air quality. It's the primary selling point, but it's a little bit about comfort and also about energy efficiency. So I won't step through each of those in detail, given we've sort of talked about some of those, but let's have a little bit more of a look at what a HRV unit looks like, in a planned form. Now you can see sort of blue zones, red zones. Red zones are extract zones, and as we mentioned, kitchen, laundry, toilet, shower are all places where we've got risk of moisture or odour. And the other blue zones that we've shown here are supply zones. Now you'll also note there's some green areas there. They're known as transition zones. So typically hallways and things like that, which we don't really need to ventilate because we're going to get air flow through those spaces from supply zones. There's a few parameters on the right there that are useful to take care of, but we won't step through each of those at the moment. What do these look like in practice? So a bit like crazy string, as someone once said. In essence, we've got on the right-hand side there, just at the bottom of the image, we've got the HRV unit, followed by some silencers, and then we move into this, what's known as a radial duct design for ventilation. So all of those are sort of small diameter pipework making up the supply and the extract ductwork. As you'll notice, it all sits under that insulation layer there. It's not insulated duct, and therefore we need to keep it tucked well within the thermal envelope for it to perform effectively. That's just a little cross-section showing essentially how they work. The important element there is that they sit under the insulation layer. If you were to run them through roof space, for example, that was uninsulated, the heat gain in summer or heat loss in winter would be fairly substantial, and you would lose most of the benefit of heat recovery. If we have a look at roughly what a system looks like, there's essentially a few components. There's a HRV unit. There is some silencers or attenuators there, and this sort of just runs you through some of the noise levels you might expect, but essentially they're a fairly important component in order to end up with nice low noise levels in your rooms. Essentially a good HRV unit should be sort of undetectable in each of those rooms. Looking really specifically at what HRV systems do and don't. So they do definitely bring fresh outside air in, and they filter that, and they do bring it up close to the internal house temperature. So some of the really good units run up around 90% efficiency. What you do need to do is not let your indoor temps drop or run away, because it is a recovery process. If your house gets really cold internally and it's cold outside, there's really nothing that saves you apart from a heater. So you need some ancillary heating. But the idea is once you've got some heat, and whether that be from solar gain or whether that be from air conditioning unit, then the HRV can operate effectively to minimise your losses. They work the same way in both summer and winter, so it's essentially heat recovery. It doesn't matter which part's hot and which part's cold. They filter to remove outside particles, as we mentioned, and also get rid of moisture and odours. What they don't do, as I mentioned, is provide heating and cooling to your building, and that's often misunderstood by sometimes early adopters or those who are just investigating the concept. So important to sort of explain that you will still need some ancillary heating or cooling. They don't have zoning capabilities. So essentially we're needing to provide continuous ventilation throughout the building. So we're needing to continually extract from that bathroom, even if you're not there, to make sure it's dried out fully. And a common misconception is that if I've got a heat recovery unit, can I put a tiny little AC system or a tiny little heating system into my building? Well, in fact, it doesn't really work like that, because the largest contribution to your heating and cooling loads are actually coming from your building fabric. So that's really a predominant thing you want to work on if you want to get your heating cooling loads down, is great building fabric. What HRV is saving you is that proportion of loss to ventilation. So if you were to bring cold air in through a window, you would need some additional heating to bring that up to temperature, which is no longer occurring when you've got a HRV unit. This is just a little bit of a checklist. I won't run through in detail, but essentially once you've got a HRV unit in a relatively airtight building, and you want that kind of airtightness to make sure you're going to get the benefits of heat recovery ventilation. If the wind rips through your building when it's cold because it's quite leaky, it's going to become really cold inside, and you've really sort of wasted your money on heat recovery ventilation. But once you've got that airtight building, you need to start thinking about other devices in there. So range hoods, for example, you need to think about whether they're going to be ducted externally or a recirculating type. The problem being with externally ducted units is suddenly the makeup air path or the replacement air in a tight building is somewhat problematic. So just a few details to think through there. The Passive House Institute, who are sort of early leaders in this sort of space for mechanical ventilation with heat recovery, have some guidance there you can have a little bit of a look through. There's also a couple of different core types for heat recovery. So if we think of a ventilation unit, it essentially has a couple of fans, a supply fan and an extract fan. It has some controls, and then it has a heat exchanger core in it. Now, they can be supplied in a couple of different types. One of those is one that only allows sensible or temperature-only exchange, and the other type is one that is known as an enthalpy core, and it can allow moisture exchange as well as temperature exchange. And we'll have a quick little look at what that might mean. Essentially, for Australia and New Zealand, the application of the moisture or the enthalpy type is really for high humidity areas. So for Australia, that's typically somewhere like Brisbane or sort of Queensland. The idea there is we've got really high moisture content during summer in our outside air, and we want to use some of the properties of the enthalpy core to strip that moisture out before it's supplied into the building. We're starting to get into some slightly more complex topics, so we won't delve too much more, but it's really just to give you an appreciation of the two different types of core. As I mentioned, Passive House, early standards and adopters of this sort of ventilation. Just to let you know, that sort of stuff is based on some of the European standards, but it's pretty similar to what we see here in our codes, in that we're aiming on the indoor air quality to sort of land between 600 to 1000 ppm. And we're looking for filtration in the old language, because it has just changed. F7 supply, M5 sort of G4 on extract. And that gives you some guidance if you look those particular grades up on particle sizes that it removes from outside air. Again, Passive House has some design methodology for these continuous rates. It's fairly important when we talk about those continuous rates that we don't oversize units, and often our building codes are not very well orientated towards continuous ventilation. Rather, particularly in a residential context, they're set up more around intermittent high volume. So we actually carried out, we being Passive House Association Australia, carried out some research in conjunction with some partners around what is the difference between that continuous low volume ventilation in terms of moisture removal versus the National Construction Code, as it's known in Australia, or deemed to satisfy rates. Deemed to satisfy rates, for those who aren't particularly familiar, is the easy path through your building code. And what we found was that the lower continuous rates actually gave lower relative humidities, resulted in lower relative humidities, which is what we want. So lots of good science supporting that. We're hopeful that there's some movement certainly in the Australian code. I know New Zealand code's already a little bit ahead in that respect on lower continuous rates. Why wouldn't you design at higher extract flow rates? Well, essentially your capital cost goes up significantly, bigger HRV unit. Overventilating actually causes excessive dehumidification, and that's not what you want either, because that can become a health problem, and it's also obviously increased operating energy. And I think that's the end for me, so I will stop sharing for the moment and I will hand back to you, Pippin.
Thanks, Joel. I was like personally designing a few passive houses and found this quite interesting. Like it was really interesting. So do any of the attendees have any questions to ask the panelists? Like if there are any, now's the time.
We've obviously done well and covered a lot of material that requires digesting.
Yeah, I
put
think
them all
so.
to sleep.
Yeah, but yeah, if that's it, then that should be sweet then, if there are no more questions. But this presentation is recorded and would be available for future watch at CIBSE.org.au. So yeah, so have a good evening, all of you.
Thank
Beautiful.
you.
Thanks,
Thanks,
Pippin.
Thank you.
Intro.
Thanks, Joel and Robin. Thank you.
Bye.
Bye.